ഓക്കെ മക്കളെ, നമുക്ക് അടുത്തതായിട്ട് എന്താണ് ഒരു ഓപ്പറേറ്റർ നോമ നമുക്ക് എന്താണെന്ന് അറിയാം. നോർമലി ഓപ്പറേറ്റർ നോമ ഡിഫൈൻഡ് ബൈ നോമ ഈക്വൾ ടു സുപ്രീം ഓവറാൾ നോമ ഓഫ് എക്സ് എച്ച് അറ്റ് എക്സ് എലമെൻറ്റ് ഓഫ് എച്ച് വിത്ത് നോം എക്സ് ലെസ് ദാൻ ഓർ ഈക്വൾ ടു. ഇത് ഓപ്പറേറ്റർ നോമിൻ്റെ ഡെഫിനിഷനാണ്. നമ്മളൊരു സെൽഫ് അഡ്ജോയിൻറ്റിൻ്റെ ഓപ്പറേറ്റർ നോമ് വേറൊരു വാല്യൂ ആയിട്ട് ഈക്വലായി മാറുന്നു എന്നുള്ളതാണ് ഈ പ്രോപ്പർട്ടി 6.1.5 പറയുന്നത്. ദാറ്റ് മീൻസ് if A is a self-adjoint operator, then norm A equal to C. Here C means supremum over all x not equal to 0 modulus of inner product x with x divided by norm x square. ഈ ഒരു വാല്യൂ ആയിട്ട്, അതായത് അതൊരു സെറ്റിൻ്റെ സുപ്രീമമാണ്. ഏതാ സെറ്റ് എന്ന് നോക്കാം. സെറ്റ് ഓഫ് ആൾ മോഡുലസ് ഓഫ് ഇന്നർ പ്രൊഡക്റ്റ് എക്സ് വിത്ത് എക്സ് ഡിവൈഡ് ബൈ നോം എക്സ് സ്ക്വയർ സച്ച് ദാറ്റ് എക്സ് എലമെൻറ്റ് ഓഫ് എച്ച് വിത്ത് എക്സ് നോട്ട് ഈക്വൾ ടു 0. ആ സെറ്റിൻ്റെ സുപ്രീമത്തെയാണ് നമ്മൾ സി എന്ന് വിളിക്കുന്നത്. ഓക്കെ, അപ്പോൾ ഈ സി തന്നെയാണ് നോം എ എന്ന് നമുക്ക് പ്രൂവ് ചെയ്യണം. അതിനുവേണ്ടി ഫസ്റ്റ് വി സപ്പോസ് എ ഈസ് എ സെൽഫ് അഡ്ജോയിൻറ്റ് ഓപ്പറേറ്റർ. ദാറ്റ് മീൻസ് എ ഈക്വൾ ടു എ സ്റ്റാർ and consider the value C as supremum over all x not equal to 0 modulus of inner product x with x divided by norm x square. We claim that our operator norm coincide with this C. If A equal to 0, then nothing to prove, because if A equal to 0, then inner product x with x is equal to 0 for all x. Therefore, modulus of inner product x with x is equal to 0. That means the supremum of the set of all modulus of inner product x with x divided by norm x square equal to 0. Therefore, C equal to 0. Okay. Next, we consider A not equal to 0. That means norm A not equal to 0. In this case, we need to prove C equal to norm A, or C coincide with the norm A. First, we will prove C should be less than or equal to norm A. For that purpose, we consider modulus of inner product x with y. By the Cauchy's inequality, this should be less than or equal to norm x into norm y for every x comma y element of h. Next, we consider modulus of inner product x with x. That is also less than or equal to norm ax into norm x. But the property of the boundary linear operator norm ax should be less than or equal to norm a into norm x. So put here, we get what that inequality becomes less than or equal to norm a into norm x into norm x. That means norm a into norm x square. Therefore, modulus of inner product x with x divided by norm x square should be less than or equal to norm a. This is true for every x not equal to 0. That means that norm a is an upper bound for the set of all modulus of inner product x with x divided by norm x square, comma x not equal to 0 and x element of h. Supremum should be less than or equal to norm a means here supremum is what? C. C is less than or equal to norm a. That is equation number 1. Next, we claim that C greater than or equal to norm a. For that purpose, we consider an equation inner product x plus y with x plus y minus inner product x minus y, a of x minus y with x minus y by the property of the inner product. This is equal to inner product x plus ay with x plus y minus inner product x minus ay with x minus y. Just distribute, apply the property of inner product x with x plus inner product x with y plus inner product ay with x plus inner product ay with y minus inner ax with x minus of minus plus inner product x with y plus inner product ay with x minus inner product ay with ay. Here inner product ax with x and ay with y cancel due to negative condition is also there. So this is equal to 2 times inner product x with y plus 2 times ay with x. That is equal to 2 times inner product x with y plus inner product ay with x. Okay. Now consider the reverse of reverse category and take the modulus on both sides. We get 2 times modulus of the RHS. That means modulus of inner product x with y plus inner product ay with x, which is equal to modulus of the LHS. That means modulus of inner product x plus y with x plus y minus inner product x minus a of x minus y with x minus y. Next, we apply the triangle inequality here. That is less than or equal to modulus of inner product x plus y with x plus y plus modulus of a of x minus y with x minus y. Okay. But modulus of that value is, and you have the definition of C. Here C is equal to supremum over all x not equal to 0 with the modulus of inner product x with x divided by norm x square. Therefore, C into norm x square which is equal to supreme over x not equal to 0 modulus of inner product x with x. So that value is less than or equal to supremum over of that value. Supremum of that value means c into norm x plus y square plus c into norm x minus y square. Therefore, we get 2 times modulus of inner product x with y plus ay with x is less than or equal to c into norm x plus y square plus norm x minus y square. Apply the parallelogram law here because it is a Hilbert space. We get what? C into 2 times norm x square plus norm y square because it is a Hilbertian norm. Therefore, modulus of inner product x with y plus inner product y with x should be less than or equal to c into norm x square plus norm y square. We take x as a point. This is true for all x and y. So, we consider x is a member of H with norm x is equal to 1 and y is equal to ax divided by norm x. Then norm y is also equal to 1. So, you got what? Modulus of it, and just substitute the values of x and y in this equation, the above equation 2. So, you got what? Modulus of inner product x with x divided by norm x plus inner product x with norm x with there is an error I think inner product x by norm x with x that should be less than or equal to c into 1 plus 1 because norm x is equal to 1 and norm y is equal to 1, that is 2c. Therefore, modulus of inner product ax with ax divided by norm x plus ax with ax divided by norm x less than or equal to 2c. Norm x square norm ax square divided by norm x plus norm x square divided by norm x should be less than or equal to 2c. That means norm x plus norm x plus r equal to 2c. That means 2 times norm x plus r equal to 2c. That means norm x plus r equal to c. Now, therefore, we got what? Norm ax should be less than or equal to c for all x. Taking supremum over all norm x less than or equal to 1, the LHS becomes norm a less than or equal to c. That means c acts as an upper bound of the set of all norm of x such that x element of h with norm x less than or equal to 1. Therefore, norm a less than or equal to c. This is equation number 3. From 1, 9, 3 we get c is equal to norm a. This is a very important result here because you can redefine our norm of a self-adjoint operator in terms of this c. That means the norm of a self-adjoint operator can be defined in terms of the inner product. Okay. Next, this is a characterization of the symmetric operator. If A is symmetric, then Ax with x is a real number and vice versa. This is a very important result. So, we first suppose A is a symmetric operator. We need to prove Ax with x is a real number. Now, consider inner product Ax with y is equal to inner product x with ay. This is the definition of the symmetry. We claim that Ax with x is a real number. Now, consider inner product Ax with x which is equal to inner product x with ax because A is self-adjoint. But by the property of the conjugacy of the inner product, the RHS is the conjugate of Ax with x. Therefore, inner product Ax with x is equal to inner product Ax with x whole conjugate. That means a number coincide with its conjugate means it should be a real number. Therefore, inner product Ax with x is a real number. Next, we prove the converse part. So, we suppose inner product Ax with x is a real number. What we have to prove here? A is a symmetric operator. For that purpose, we consider an equation 4 times inner product Ax with y, which is equal to inner product A of x plus y with x plus y minus A of x minus y with x minus y plus I into inner product A of x plus iy with x plus iy minus I into A of x minus iy with x minus iy. You can get the LHS using the RHS. So, we consider the RHS, then we will get the LHS. Next, we change the position of x and y in the above equation, and then we get 4 times A of y with x is equal to A of x plus y, or we can consider y plus x here, but addition is commutative, so you can write y plus x as x plus y. In the second case, A of x minus y, actually A of y minus x with y minus y, but we can take the minus of this on both sides, and minus 1 is a real number, so minus 1 into minus 1 becomes plus 1. So, you get what? A of x minus y with x minus y equal to A of y minus x with y minus y. So, we applied that here, and then the next term is I into inner product A of y plus ix with y plus ix minus I into A of y minus ix with y minus ix. Taking the conjugates of this inequality on both sides, we get 4 times a of inner product a of y with x conjugate equal to first term is a real number by the assumption, its conjugate coincide with itself. Second number is also a real number. Third one and fourth one all are real numbers, so they coincide with itself. Therefore 4 times inner product, and the LHS is what actually 4 times inner product ay with x conjugate, but that is equal to inner product x with the ay. Therefore 4 times inner product x with the ay is equal to a of x plus 5 with x plus 5 minus a of x minus 5 with x minus 5 minus I into a of y plus ix with y plus ix plus minus into I conjugate is minus I, minus into minus is plus itself. Therefore and I conjugate is minus I. We applied this in the equation. So you got inner product ax plus y with x plus y minus a of x minus y with x minus y minus I into a of x minus iy with I into x minus y. Actually we take I outside, and plus I into inner product minus I into a of x plus iy minus I into a of minus I into x plus iy. That is equal to inner product a of x plus y with x plus y minus a of x minus y with x minus y minus I into actually I from the first part and the I from the second part. Therefore I into I conjugate, that is equal to minus I square. I into I conjugate is 1, actually 1, because I square is equal to minus 1. Minus of minus 1 is actually 1 itself. And in second case also we will get minus I into minus I, that is minus I square. Minus 1 minus 1, I square is minus 1, and that is equal to we will get minus 1. Therefore 4 times inner product x with ay equal to 4 times ax with y. Therefore 4 times inner product x with ay equal to 4 times ax with y. That means x with ay coincide with ax with y. Therefore our operator A is a symmetric operator because A equal to A star. This is a good result. This is a characterization of the self-adjoint operator or a symmetric operator. And the next one is a very crucial result. A be a symmetric operator and norm Ax equal to inner product x Ax with x whole raised to 1 by 2. That is given actually. And norm A equal to mu, which is equal to supremum of modulus of inner product Ax with x with norm x is equal to 1. That is actually the definition of the norm from the above propositions or properties. Okay, that means you are given a symmetric operator with a condition norm Ax is equal to inner product Ax with x whole raised to 1 by 2. Then norm A or minus norm A, either norm A or minus norm A is a spectral value. That is what we have to prove here. അതായത് ഒരു ഓപ്പറേറ്റർ സിമെട്രിക് ഓപ്പറേറ്റർ ആവുകയും അതിലൊരു അഡീഷണൽ കണ്ടീഷൻ നോം എ എക്സ് ഇസ് ഈക്വൽ ടു ഇന്നർ പ്രൊഡക്റ്റ് എ എക്സ് വിത്ത് എക്സ് ഹോൾ റേസ് ടു 1 by 2 പ്രോപ്പർട്ടിയും ഉണ്ടെങ്കിൽ നോം എ എന്ന് പറയുന്നത് നോം എയോ അല്ലെങ്കിൽ അതിൻ്റെ നെഗറ്റീവോ മസ്റ്റായിട്ടൊരു സ്പെക്ട്രൽ വാല്യൂ ആണെന്ന് പ്രൂവ് ചെയ്യണം. അതാണ് ഈ തീർച്ചയായും പറയുന്നത്. അറ്റ്ലീസ്റ്റ് 1 of mu or minus mu is a element of sigma of A. For that purpose, we suppose our operator is a symmetric operator and consider norm A equal to the definition supremum over modulus of inner product Ax with norm x is equal to 1. We need to prove is either mu or minus mu is a spectral value or a member of sigma of A. But here norm A is the supremum of modulus of inner product Ax with norm x is equal to 1. Then by the definition of the supremum, mu is the supremum of a set means there is a sequence in that set in which that sequence converges to mu. So we can have a sequence xn in H with norm xn is equal to 1 and modulus of inner product axn with xn converges to norm A or mu. Okay, so we need to prove what lambda equal to plus or minus mu is a eigen, either plus mu or minus mu is an eigen value. Okay, since inner product axn with x is a real and bounded sequence, modulus of that value tends to norm A and axn with xn should be a real number. That's by our above proposition. A real sequence which is bounded and it is absolutely convergent, then by the Bolzano-Weierstrass theorem, it has a convergent subsequence. Therefore, there is a subsequence xn k of xn with norm xn k equal to 1 and inner product of xn k with xn k converges to lambda. Lambda is either plus mu or minus mu. Okay, therefore the modulus of that value should converges to mod lambda. Mod lambda equal to what? Mu. Mod lambda equal to our norm A. Okay. By the uniqueness of limit, but by the above part we have no modulus of inner product xn with xn tends to mu here, which converges to mod lambda. Therefore mod lambda equal to mu, that means lambda equal to plus or minus mu. So we consider a result that modulus of the 0 less than or equal to norm of axn minus lambda xn square, because it is a norm value is always greater or equal to 0. So you can take the any norm. Here we consider axn minus lambda xn. Here lambda I is our limit and xn is the corresponding sequence. So we need to prove what lambda is either a eigenvalue or a residue spectrum value or a continuous spectrum value. Either sigma p of member of sigma p of A or sigma c of A or sigma r of A, or simply a member of sigma of A. That means A minus lambda I is either not injective or it is injective with its closure coincide, its image closure coincide with H, or it is not dense in H. Okay, three possibilities are there. So we consider norm of axn minus lambda xn square. By the definition of the norm, that is equal to inner product axn minus lambda xn with axn minus lambda xn. Just apply the linearity properties of the conjugate linearity and linearity of the operator here. So axn with axn minus axn with lambda xn minus lambda xn with axn plus lambda xn with lambda xn. Axn with axn is actually norm square minus 2 times axn with xn plus lambda xn with lambda xn is coincide with mod lambda square into norm xn square, which is equal to norm of axn square minus 2 lambda into axn with xn plus norm x square. But axn with xn is what? Axn with 0 less than or equal to norm of axn square. This is true for xn k also. That means 0 less than or equal to the norm of a minus xn k minus axn k minus lambda xn k square. That is equal to norm of axn square minus 2 lambda into axn k with axn k plus mod lambda square, because norm xn square equal to 1. But you know axn k with xn k, the inner product of axn k with xn k equal to norm axn k square by our assumption. That means axn square minus 2 lambda into axn k square plus mod lambda, but apply the limit on both sides, we get axn k minus xn k square that tends to lambda. Inner product axn k with xn k tends to lambda. That means 2 minus 2 lambda square plus mod lambda square, but lambda is a real number because modulus value is a real number, its limit should be a real number. Therefore lambda is a real number. Mod lambda square coincide with lambda square. Therefore, we get norm of Ax and k minus 2 lambda square plus lambda square, that is less than or equal to norm A square into norm Axn square. Just apply the property of a bounded linear operator here. So norm Axn k square less than or equal to norm A square into norm Xn square. Just substitute that. We get norm Xn square minus 2 lambda square plus lambda square less than or equal to norm A square into norm Xn k square minus lambda square. Norm A square equal to lambda square, norm Xn square equal to 1, that means lambda square minus lambda square or mu square minus lambda square. Mu square and lambda square coincides, therefore that is equal to 0, or which tends to 0, actually not equal to 0, which tends to 0. Therefore norm of Ax and k minus lambda Xn square tends to 0. Norm of a square, norm square tends to 0 means norm tends to 0, that means the inner value tends to 0. Actually here 0, Axn minus lambda Xn tends to 0, but here there is an error, it is not infinity, actually this is 0. Axn minus lambda Xn tends to 0, that means a minus lambda I of Xn tends to 0. That means that limit tends to 0 means either a minus lambda is not injective, that means or it is injective with the image is dense in a minus, the image of a minus lambda is dense in H. That means either a continuous spectrum value or a residue spectrum value or a eigen spectrum value. That means in toto lambda must be a member of sigma of A. This is a very important result. Okay.